Alright guys, I was trying to find the best way to go over mini quiz number 1 with you, so I think what I'm going to do here is I've got it all downloaded into a smart file, and I think we're just going to walk through it and record this and kind of see how all this goes. Alright, so the first thing I have for you right here is the answers to the 4 multiple choice questions. I'm hoping that you guys can go through and see what your responses were on that Google form there. In the future, you'll still have the picture of what it was that you submitted, so I think that'll be a little bit easier. But all right, so just going through here, the 4 answers were A and C and D to each of those 4 problems, and I want to walk through them all with you as quickly as we can. Remember that the non-calculator questions are supposed to take about 2 minutes apiece. The calculator questions are supposed to be about 3 minutes. So let's take a look at what's going on here in number 1. We've got a function f here that's shown above, and they want to know at which value of f the function is continuous but not differentiable. And the answer to this one was going to be A. As we walk through it here, and we think about what's happening at this particular graph right here, we can see that the function is continuous at A because its left-hand limit and its right-hand limit are both approaching the same value, and that value is equal to the value of f of A. There's no open dot there at A. It's not differentiable, though, because if we were to think about the tangent lines, the left-hand derivative would be a very steep positive number, but the right-hand derivative would be a pretty steep negative number. So basically, we come to this unnatural connection right here called a cusp at point A, where 2 curves come together unnaturally, and that means that our function is not differentiable at that particular spot. As we go through the other 4 choices real quick, we can see why those are not the case. B is not the answer, because at this spot right over here, our function is not continuous. The left and right hand limits are the same, but because of that dot right there, the value of f of b is not equal to the limit as f approaches b. At C, this is actually the most normal point on the graph. Nothing weird is happening here. So at that spot, the function f is continuous and differentiable. At D, we've got a left-hand limit that's up here positive somewhere and a right-hand limit that's down here negative somewhere, so the function is not continuous at all at point D. And then at E, actually we have the same thing going on at E that we had at C. The function is both continuous and differentiable there. So A is the only spot on this graph where the function is continuous but not differentiable. On to number 2. So we've got f a function given here by f of x is equal to 2x times e to the x, and we're supposed to find where the graph of f is concave down. So hopefully this didn't concern you guys too much as to how to get it. Concavity comes from the sign of the second derivative, so we need f prime of x, and that's going to require the product rule. First factor is 2x times the derivative of the second, just e to the x, plus the second factor, e to the x, times the derivative of the first, which is just a 2. And that's it for f prime. But again, concavity comes from the second derivative. So to do f double prime of x, we need to take the derivative of each of these 2 terms independently. Well, when we go to take the derivative of the first term, which is 2x e to the x, we realize that is exactly what the original function was. So what we have right here, let me kind of underline this in yellow, that entire binomial expression is the derivative of 2x e to the x. So basically, this second derivative is going to begin with the first derivative as well. 2x times e to the x plus a 2 e to the x. And all that takes care of the derivative just of the 2x e to the x. But now we have to go plus, and now the derivative of 2 e to the x is just going to be another 2e to the x. Now that can be cleaned up just a little bit here into getting 2x times e to the x plus a 2e to the x plus another 2e to the x is going to be a 4e to the x. And if we're interested in concavity, we want to know where this function's second derivative is going to be positive and where it's going to be negative. So we're going to set that equal to 0. Sorry, guys. Set that equal to 0. And to do that, remember, this is a non-calculator question. We try to factor out what we could. We can pull out a 2 and an e to the x, and that's going to leave us then with an x here for the first term and a plus 2 for the second term. And that is going to equal 0 anytime either one of these 2 factors was equal to 0. Well, 2e to the x is an exponential function that will never equal 0. The only 0 to this function we're going to get is when x is equal to negative 2. And now from there, I don't know if I have any ability here, guys, to extend this page here at all. We'll just go to a new page to do that. So x equals -2 is the only potential point of inflection that we have right now. We want to test the concavity of that function. So what I'm going to do is go back to my second derivative here, which was f double prime of x, and the easiest place to do this would be factored form, which I believe was a 2e to the x times the quantity, let me double check that here, times the quantity of x plus 2. Okay, so there's our second derivative, and we got this thing to equal 0 when x was equal to a -2. And now if we just make a quick sign chart, and we think about what happens right here, any time that x is less than -2, like for example, x equals -3, and then maybe any time x is greater than -2, 0 would probably be the easiest. Let's think about the value of the second derivative at these spots right here, f double prime of -3. Well, 2e to any power is always going to be positive, but a -3 plus 2 is going to be negative, and a positive times a negative means that this product is going to be negative, and on this interval our graph of f is going to be concave downward. When we put in something like x equals 0, again, the 2e to any power is positive, but a 0 plus 2 is going to be positive. So here, f double prime of 0 would be positive, and on this interval, we would be concave upward. So back to the question in the last problem, we wanted to know where the graph of f was concave down, and the only spot we see that happening is here, and that's going to occur anytime that x is to the left of -2, or anytime that x is less than -2. So our answer for this one was going to be A as well. All right, let's move on to question number 3. Now, one thing I always want to remind you guys as much as I can here, just because a question is given to you in the calculator section, it does not mean that the calculator has to be used on these problems. And this is one example of a calculator question that didn't require a calculator at all. So what's going on right here? We've got regions A, B, and C in the figure above, bounded by the graph of the function of f in the x-axis. The area, they tell us, of each of those regions is 2. So we have a region of area 2 here, and a 2 here, and a 2 here. But of course, let's notice 2 of those, A and C, are underneath the x-axis, and that's going to be pretty important right here. Okay, so what's going on? They are asking us now to come up with the value of this definite integral here. The definite integral from -3 to 3 of f of x plus 1 taken with respect to x. Well, the only information we have right here, this graph, is just of the function f. That plus 1 is kind of sticking out like a sore thumb. So we're going to split this into 2 different integrals. First, an integral from -3 to 3 of just plain f of x by itself. And then what a lot of people ignore here is another definite integral from -3 to 3 of just the 1 with respect to x at the end of all that. Okay, now that first integral here from -3 to 3 of f of x, that's information we can glean from this graph right over here. So starting at -3, we have a region right here of 2, but below the x-axis, then another region of 2 above the x-axis. Those two just wipe each other out. So from -3 to 0, the value of that integral is 0. But then from 0 to +3, we've got an area of 2 below the x-axis. So that entire integral right there is going to take on a value of -2. What we have to worry about next, though, is the integral from -3 to 3 of 1 taken with respect to x. And if you think graphically about what's going on right there, the function y equals 1 is right here. It's a horizontal line. And if we started it at -3 and ended it over here at +3, we're looking at this simple rectangular region here that's above the x-axis with a height of 1 and a width of 6. So the area of that region is 6, and because it's above the x-axis, it's going to be positive. So we add together the values of these two integrals, the -2 plus 6, and that gives us 4, and our answer here for number 3 is C. Okay, let's move on to the next one right here. All right, number 4. F is going to be a function given by this, with a derivative given by this. So this is important here to note, guys, and I haven't looked real carefully, but I would bet that a lot of people who missed this problem did so because they thought that this sine graph was actually f of x rather than f prime of x. So they've given us the derivative of that function, and they want us now to figure out how many relative extrema f has on that interval. Well, if we think about any function in the world, guys, it has a relative extreme value, either a max or a min, at a spot like, for example, right here or right here or right here. And the telltale sign here is that the derivative changes sign at a relative max or a min. Right here, the derivative was negative because the function was decreasing. Then it goes positive because the function is increasing. So what we're looking for is a sign change in the derivative of this function. So what I did here is I took a moment here and I graphed, and I'm very impressed with myself right here. I just got the Inspire CAS app for free on the iPad, so you guys might want to check that out. It would work on your phone too, I think. But I went ahead and graphed what, remember guys, is the derivative of this function, f prime of x, which was the sine of x squared plus 1. It gave us this whole graph, but we were really only interested in what happened on an interval from 2 to 4. So, it took me a while to play around with this here, but if I go to Tools right here and then go to Window or Zoom and Window Settings, this is all the same stuff as your calculator will do by hand, just a slightly different interface. We just wanted to start this thing when x was 2, and we wanted to, let's see here, end this interval when x was 4. I don't think anything else is really all that important right there. So when we hit OK, this is what we have now for the graph of our derivative. And what we were interested in, f has a relative extreme, a minimum or a maximum, when the derivative of f prime, which is what we're looking at right here, changes sign. Well, what we can see here, and I don't think I can hit anything on the graph right here, guys, but we've got a spot right over here where the derivative changes from negative to positive. Okay, there's another one right about here in the middle of that graph right there. Oh, and now I have erased everything. How did I do that? Where's the undo button, guys? Okay, now I've really done it. I didn't just delete that, did I? Well, here I was so proud of myself. All right, let's try that again. Sorry, everybody. So this was the sine of x squared and then a plus 1. And we'll go back to this right here. I messed with my window just a little bit right here, and I think that's going to be important, so I think I better go back and check that here. So we were... Oh, for crying out loud. All right, from an x value of 2, okay, gotcha. And then from there, we're taking that to an x value of 4 by itself, and let's hit OK. So again, we were looking for spots here where the derivative, this graph right here, was changing signs, and it happened 1, 2, 3, 4 times on this particular interval. So if I go back to where we were here just a second ago, there were 4 spots there where that graph, the derivative, changed sign. So our answer here for this one was going to be D for that last one right there. Okay, I'm going to stop the video right there, and then we'll come back and we'll do the free response question